Welcome to the first video in the Real Analysis video series, and as promised, I am going to be skipping chapter 1 on all of that sort of preliminary stuff on logic and set theory, and we're going straight to, well, actually kind of an awkward subject, the axioms. It's a little hard to explain what the axioms are and like what we are doing with these things right up at the start. I hope it kind of sinks in a little bit better over time, but I'll try my best to make it make sense. First of all, here's a preface that I think maybe guides you in thinking about the axioms and thinking about all of chapter 2. What you should imagine is that we are trying to construct everything in mathematics from a very explicit foundation of assumptions. All right, so there's like some collection of assumptions. They're called the axioms of set theory. You don't really need to know that, but there is some very widely accepted set of assumptions upon which I'm going to maybe oversimplify the story here a little bit, but all of modern mathematics is founded upon. Okay. We would like to construct the theory of real numbers and functions of a real number from those axioms. Now, if we really went all the way down to the axioms of set theory, that is so far down the ladder towards the foundations of this edifice that it would take forever to get from there to just the very first lesson in real numbers. So we don't want to go through all of that. Those other foundation construction steps are for a course in set theory. We are going to pick up the story at the point where we imagine we have already constructed from the axioms of set theory, the natural numbers, integers, rational numbers. So we basically, right throughout this course, you should basically assume that famous facts about rational numbers can be used without proof because we've already built them and you imagine we've already studied them and we know them. So we don't need to justify anything about rational numbers, but we don't yet know anything about the real numbers. We don't even know about their existence. So that's our initial job, is from the perspective of a kind of total knowledge about rational numbers and a complete lack of knowledge about the real numbers, we would like to construct the real numbers. And then of course, once we know what the real numbers are, we can start talking about functions of real numbers and so on. Part of that project is to say exactly what it is that we are trying to construct. And that involves the axioms of real numbers, right? So these axioms are not quite like the axioms of set theory in that we typically sort of treat the axioms of set theory as something that we assume to be true, and they form a kind of foundation of mathematics. These, right, when we talk about these axioms, we don't necessarily assume that they are true. These seem to act more like a list of demands. So, we are going to require that, once we construct the real numbers, we need to check what we have constructed to make sure that it satisfies all of these axioms, right? So this is kind of like if what you built doesn't have these properties, then we're not willing to call that the real numbers, that you weren't successful in constructing the real numbers, because whatever we call the real numbers needs to have these minimal properties. So that's what these axioms are. I hope that makes sense. And I'm going to go over these somewhat quickly, only because they involve these terms and concepts like commutative, associative, identity, inverses, and so on. And these concepts come up in discrete mathematics, and I don't want to be too repetitive. I don't want to explain these ideas in the discrete mathematics course and then also describe them here and have all of this overlap and wasted time. So I'm simply going to refer you, if you don't already know what these words mean, I'm going to refer you to the discrete mathematics sections and videos where these are defined and studied. It should be somewhere in the in the set theory portion of the discrete mathematics course, I believe, although I could be wrong about that. But I haven't even built out that part of the discrete mathematics video series as I record this video, so I don't yet know where it lives in that series. So here's the deal. If you watch this video and you want to know where the videos are that explain these things in the discrete mathematics course, then leave a comment and hopefully I'll have time to go look, because by the time I record those videos in discrete mathematics, I'll have forgotten that I wanted to link them here. So leave a comment, remind me, and I may, if I have time, go find where they are in the discrete math playlist. But okay, so anyway, and I am noticing, by the way, that I left off a possibly important property of addition, which is closure, right? So closure. It may actually not be terribly important that I mention closure explicitly, because if we say that this is an operation, then sometimes some mathematicians take the very word operation to imply closure. So, well, why not say it explicitly, just to be on the safe side? But maybe it's also fine if I didn't say it. But in any case, so what we require, and by the way, these are called the complete ordered field axioms, right? So the complete ordered field axioms specify the real numbers. And here's a little funny thing. A set, which we denote by this double struck R symbol, is called the real numbers. What? A set is called the real numbers? How does that make any sense? Well, I think it will make a little bit more sense later on, but I just wanted to flag and acknowledge that already something quite odd is going on there. But in any case, so let this be any set. We call it the real numbers if it satisfies all of these axioms that are listed below, and jointly they are called the complete ordered field axioms. I want to maybe just point out, because it's kind of a neat little idea or note, that there are just the field axioms, and lots of things. For instance, the rational numbers, certain classes of matrices, and lots of other things, very important things, satisfy the field axioms. And so it's just a useful concept, the concept of the field axioms, right? But many things, right? And like a lot of those things we would not call the real numbers. So it's not yet specific enough for us to have pinned down the concept of the real numbers. So then you go further and you make more requirements. You require that this thing be ordered in a special sort of way that we'll discuss in a minute. But that gets you the ordered field axioms, and that is still satisfied by the rational numbers. So even there, you don't yet have something specific enough to capture the concept of the real numbers. So that's where this last requirement of completeness comes in, and once you have all of those properties, that is now specific enough for us to say that, yes, this is the real numbers. This gives us all the properties that we wanted and demand for anything that we would call the real numbers. Okay, so again, right, not talking about these things in terrible detail, then I'm just going to sort of gloss over this and say that, well, we've got this requirement for addition, which is that it be commutative associative, have an identity, which we use the symbol 0 to denote its identity element for addition. And minus x is the symbol for inverses, and every element must have an additive inverse. Multiplication, written by a dot, is commutative associative, has its own identity, which has its own symbol, 1. 1 is not equal to 0. I think that makes good sense. And every number has a multiplicative inverse except for 0. And that kind of makes sense, right? We write the multiplicative inverse as x to the negative 1. We somewhat commonly understand this to mean 1 divided by x. And certainly you would not want that kind of a thing defined when x is 0. So, okay. So there are the requirements that we have, right? We make these demands on any set that we would call the real numbers. Multiplication distributes over addition. So what that means is that if you pick any x, any y, any z, and you write this down, then it should also be the same as this right here. So that's the distribution of multiplication over addition. anything that we would be willing to call the real numbers and also willing to call its addition and multiplication operations. But right, and by the way, I guess this I think goes without saying, but sometimes I'll explicitly write the dot for the multiplication and sometimes I won't, but it's implied if I don't write it. So anyway, anything that we would call the real numbers must satisfy this property for every possible choice of x, y, and z out of the set. Okay. Now on to the order axioms, and this says that the less than or equal to relation must be a linear order, another concept that is studied in the discrete math series. All addition and multiplication by positives. By the way, this is, I don't even know what's going to be in the discrete math series, so this one might not be. Because we're kind of building this all up from scratch, we actually have to say what it means for a number to be positive. And we'll say that it is positive if it is strictly greater than 0. So that's like our definition of a positive number. And so then what this property is saying is that if you take any two numbers that are ordered, right, x and y, let's say, or actually since I've got x up there, let me say y and z. So if y and z are ordered like this, then addition preserves order, which means that if you say add w plus y, then that is less than z plus, set it out of order, but you get what I mean. So adding the same thing to both sides of an inequality preserves the ordering, so to speak, right? It's still ordered with y to the left of z, basically. So anyway, that is the idea that addition preserves order. And then also multiplication by positives also preserves order. So, so here with x being strictly greater than 0, we would also get that xy is less than xz, right? So multiplication by positives also preserves order. That is a requirement that we would have for anything that we'd be willing to call a set of real numbers with an ordering relation. Okay, but as I mentioned, the field axioms together with the order axioms are called, anything satisfying those is called an ordered field, and the rational numbers, not the real, also the real, but also the rational numbers are an ordered field, and so it's not yet enough, right? We don't have enough properties to pick out the real numbers, and so that's why we further need the completeness axiom. This is satisfied by the real numbers, but not satisfied by the rational numbers. We will actually study that. I think we'll even state and prove that at some point, I believe. But in any case, at least for now, you just need to know what this completeness axiom is. It says that if x is entirely below the set y, I am making up on the spot this way of talking. I think it makes sense, but just know that it's not officially defined, and I don't think I've ever seen anybody else speak that way. But I'm doing it to be brief and to be descriptive. So let me go ahead and be explicit so that you can translate between these sort of informal and formal language. So what I mean when I say that x is entirely below the set y is that for all x in x and y in y, x is, you probably could have guessed what I meant, but there you have it. So whenever x is entirely below the set y, then there is at least one element c, and c, of course, must be some real number, but okay, sure. There is at least one real number which is between them. What do I mean by between them? Well, I mean that for all x in x, x is less than or equal to c. So actually what I kind of mean is that c is an upper bound of x. We'll talk more about upper bounds in a minute, but you can see it kind of already. And for all y in y, c is a lower bound of y. So that is the completeness axiom. And well, here I marked that it's the Lub property. I'll explain a little bit more about what I mean by that later. But actually, that's kind of correct, but it's, now that I think about it, it's a little bit not totally correct. The correct statement is that the completeness axiom implies the Lub property, and the Lub property implies the completeness axiom, so that they are equivalent to each other, but they're not the same. So maybe putting this here is slightly technically wrong, but oh well, it's fine. I don't think anybody's going to be particularly confused on that issue. Yeah, this is a pretty long video. Although I haven't yet gotten to an exercise, and that was my intended design for these videos, probably it's better to keep them short. So I'm just going to end the video here, and we'll pick this up on the next video.